what did we do now? So we have these contracts, we created this ballot, we created a proposal, we voted for proposal, and anybody can actually do the same. So because this is all in Remix and it's nice for testing, we also want like our users to interact with this. So we also build the whole front end for it and connect it to the back end blockchain. So can we go to the... we will need the address, so we can copy it, yes. It's a bit confusing, I'm sorry. Okay, so this is like the admin interface of the app. So you enter the address and you submit, and this will basically connect your app to this contract, to the award token. And as you can see, this was created in Remix, and so Remix voting, you open this, just like have MetaMask open and Robson network, and then you can create one proposal. You can create only one proposal and you can vote only once. So that's why he's switching now the account so that he can create a new one. Here we don't need the strings. This is like for Remix, if you want some improvements, you can actually post like some ideas of how we could make things better. Okay. So this is now exactly the same as in the UI in the Remix, yes. Okay, pending again, but in the meanwhile, we can just see how, when you build your front end, how do you connect it even with blockchain? So, it's already there. Awesome. Can we check the code, Alex? Okay. So one contract, second contract, this is the UI. How does this all come together? Let's go. We are using Web3. This is like the way to interact with Ethereum network for JavaScript. If you use some other languages, you can use another modules. What you need to set a current provider. It's like, here it's a MetaMask in this case, and you also need to fetch the address of the user so that when he votes, you will be able to see who voted and to identify the person. Then we need to copy the ABI of the contract. Contract has some certain structure, and if you go to Remix and click in the Compile tab, do we still have it open? In the Compile tab, you have a Details button, and there you can basically just copy the ABI. Everything is ready, you just click, copy the value, and you also paste it somewhere in your app, because this is what the app needs. Okay. What else do we need in the app to make it connected? So we need ABI, and we need to copy the link to the deployed contract, the address. So as you, this is where you can copy it from below, where you create the instance in the Run tab. This is the address below of the contract, and you just click and copy, and this is also something that you need. And I think this is basically more or less it. And then you get some methods through Web3, and then you can basically, you can see the method vote, and this is the transaction, so it's payable, but then you have also calls that are just read-only, and these are for free, so you can always just execute them. Okay, so did somebody vote, or did something? Can we check? No. Nobody? Okay. So you can play with this at home. If somebody wants to recreate this, go ahead. I mean, it's open source. If you want to use it for any of your project or something, it's free to use. And thank you very much for your attention.
All right. Muchas gracias, señorita. Wizard Amigos es fantastico. All right. Up next, without delay, Martin Wander BC, who's going to talk about unifying communication semantics of distributed programs.
Oh, do I have the clicker? Thank you. Hi, I'm Martin BZ. Yeah, so I'm going to talk about communication. See if the clicker works. There we go. Oh, go back. Ah, there we go. /wander on GitHub. All right, conversations. Humans have conversations, and generally what they try to do is come to share some shared understanding. And I'm going to talk about not just human conversations, but how we can communicate these ideas. So with humans, we have several different mediums, like verbal, which then breaks down into written and oral, and nonverbal, which is like body language, and telepathy. Yeah. So how do programs conversate? Traditional programs, this is for like Linux and Unix, System 5. We have signals, pipes, sockets, message queues, semaphores. There's a lot of different ways two programs on a computer can talk to each other. And it doesn't really matter if you don't understand what these are. I'm just putting out that there's a lot of different methods, and we'll talk a little bit more about them later. So, Ethereum contracts. Ethereum contracts are like the first program on a blockchain, right? So how do these programs communicate? Well, currently there's only really one method, and that is atomic synchronous calls. So what is a synchronous call? So this graph shows the lifeline of 3 programs. Program A is running, then it makes a call, which is like, program A is like saying something to program B, all right? Giving it some information. B receives it and starts running. And when that happens, A freezes. Then B may make a call to C. And when it does that, B and A are frozen. Then C, and when it's done, is going to return some information to B. B might do something with that information, then it's going to return it to A. So that's what it means to be synchronous. Like when one program talks to the other program, it freezes or blocks. So what does atomic mean? Well, it means when A, if it has some state, something that changes, right? Maybe it stores something. That's what we refer to as a state. When A calls B, we have to keep around A's state and B's state. And then when B calls C, we have to keep around A, B, and C's state. And then when C returns to B, we also have to keep around A, B, C's state. And then finally, when B returns to A, we have to keep around A, B, C's state. And then finally, when A is done running, we can either save this state, or if B crashes or A crashes, then we throw all that away. So either everything works or nothing works, right? It's the end result of atomic. So with blockchain computers, we have sort of this weird problem. Like when it comes, for Ethereum contracts talking to other Ethereum contracts, so far this is, worked out. But like what happens if a blockchain, what happens to the blockchain running, and how does a computer program communicate to each and local programs? So for example, we might want our blockchain computer to talk to our local computer or vice versa. So doing that synchronously and atomically doesn't quite make sense here. Here's how computers currently, local programs currently talk to the blockchain. You send in a transaction, the transaction gets included in the block, then you get a transaction receipt to your computer. And that's different from an asynchronous or atomic communication. It's neither of those things. So atomic synchronous calls run into some problems here when we want to communicate outside of the blockchain. For one, they break down when we have high latency. So when a computer program talks to a program on a blockchain, there's going to be a lot of latency. It's going to take a while for the computer program to get a response. And the reason that's a problem is because full atomicity is expensive. Imagine if our local program had to keep all of its state around in memory until it got a response. Maybe it was even dependent on other states. So holding that around a lot of times is unnecessary. Not all the time, but a lot of the time. Yeah, and it's hard to interpolate with existing systems, because that's not the way most programs work today. So an alternative to atomic and synchronous calls are synchronous calls. So remember before, when A sent a message to B, A was stuck. It couldn't run, it had a block. But with synchronous computation, A can send a message to B, and it's free to do something else now. It may get another message and start running again. B then can send a message to C and exit, also do more stuff, etc. Yep. So to sort of build a taxonomy of the different systems, synchronous communication happens with Ethereum contracts and blocking inter-process communication. Asynchronous, so PC to blockchain or blockchain to PC, that's always asynchronous with sending a transaction and getting a receipt. Non-blocking inter-process communication, most cross-shard communication schemes are asynchronous, and humans. It'd be really funny, or it'd be slightly odd if I was having a conversation and said something, and then immediately after I said something, I just totally froze until the other party in the conversation responded. Yeah. And when it comes to atomicity, we sort of have the same dichotomy. We have Ethereum contracts and DPs, databases that usually have some form of atomicity, but most other communication styles are non-atomic, so PC to blockchain, cross-shard, non-blocking IPC, and blocking IPC in humans. So asynchronous non-atomic messaging is sort of like the lowest common denominator for everything here. But it has some problems, right? So sometimes we do need atomicity, right? So if we start off with this primitive of atomic, non-atomic asynchronous communication, one question is, can we build atomicity on top of it? This is kind of known as the train in the hotel problem. And the idea is, if I'm trying to book a ticket with a hotel and book a ticket on a train at the same time, how do I do this in an asynchronous system? The other problem that gets brought up often is it adds developer complexity, because it's harder for people to think about. So to address the train and hotel problem, so these were supposed to be white lines here. There's actually black lines here. I don't know if you can see them. Anyways, the blue dot is someone who is trying to order the plane and the train ticket and the hotel ticket at the same time. The yellow dot on the top is the train contract, and the bottom one is the hotel contract. So what's going to happen is the managing contract, transaction managing contract, is going to send a message both to the train and hotel contract asking them if they can get a ticket, right? And the train contract, and if everything goes good, and the hotel contract will send back a response, yes. And they will reserve the tickets for the person. Then once the managing contract gets back those two responses, it will send another message to both of these contracts to commit. And this is the basis of what's called a two-phase commit. And there is many, many different formalizations of two-phase commits, and different ones are work different for your application. But the point here is it's solvable to build atomic transactions out of non-atomic base components. And like another intuition to this is you can think that really everything we build on is ultimately at the root level in distributed systems is TCP, which is asynchronous and non-atomic, right? So we've already learned how to turn something that was asynchronous and non-atomic into something that's synchronous and non-atomic, or atomic. So the fact that we could replicate this, again, is not really surprising. So the other problem is developer complexity. If you come from JavaScript, you might be familiar with callback hell. So where you get lots of callbacks inside callbacks inside callbacks. And I think this is mostly, well, for a large part, can be solved by promises and primitives like async and await. So if you don't know what those things are, it's fine. What this means, though, is it's a high-level abstract. Underneath, things are still happening asynchronously, but we provide a way so you can structure your logic so it still looks like it's happening synchronously, right? So you still can reason about things in the same way. Yeah, so it provides logical synchrony. So I think the end result is that from the taxonomy sort of looks like this. Asynchronous non-atomic messages are the smallest base components of everything, right? They're smallest unit that we have. It's the smallest primitive. Then from that, we can build atomic things, structures, and we also can provide logical synchronous structures. So it looks logically like it's synchronous. So yeah, for that reason, I think like asynchronous non-atomic messaging is a better abstraction for how our programs should communicate. So with synchronous messaging in Ethereum, it's like tightly coupled. We really don't have to think about how messages are handled because it's just built in. Only one program can execute at a time. But now if we have asynchronous messaging, that means multiple programs can be executing at any given time. And that means multiple programs can be sending multiple messages to a single program. So we need a way to handle messages, or a model. And this can be thought of in human terms too. Like multiple people can be having conversations at the same time. Multiple people can be trying to have conversations with the same person at the same time. That doesn't really work out very well though. So one model or one way to handle messages is called the actor model. And it's a very simple model. And I like it because you can think of it in physical terms. So to describe what it is, what actors have are a mailbox, some storage, and an address, kind of like your house. And what actors do, they can create more actors, send messages to other actors, and designate what to do with the next message. And that's all the actor model is. You can sort of visualize it like this, right? I have an actor, and it can spawn other actors. And actors can send queue messages on other actors' inboxes, etc. So in the blockchain world, we have a few differences, though. Things have to be deterministic. In pure actor model, things are non-deterministic. And one nice thing about the actor model is you automatically avoid weird situations like reentry bugs. So with synchronous calls, you get into a situation where A calls B, and B might call A, and then now we have two instances of A running at the same time, and they could be both mutilating the same state, and that can cause confusion in the program. So with the actor model, what would happen is A would call B and continue running to completion. Then if B called A again, what would happen is it would not start up a new instance of A, but it would that message would get processed after the first instance was done running. So lastly, who can talk to who? So we might have a program with two functions, and main and foo. And program A might have a reference to program B's function. And a program here can only talk to a program if it has a reference to. This is the address in the actor model, if you will. Not only that, but programs can share references to each other. So if A has a reference to C and to B, A can give the reference to C to B, and now B can talk to C. And the reason we don't want to let everyone talk to everyone, so in Ethereum, everyone can talk to everyone, right? So if you constrain it to who has references to who, you can build isolation, right? You can build contracts that are protected by who has the reference. So this authentication contract has a reference to the logic and database contract, but no one else does. So we know that these contracts here, we don't have to worry about writing logic to protect them from any other malicious attacks or malicious messages, right? The only thing we have to worry about is the authentication contract. So we can focus our effort on auditing that. That in isolation allows us to build more modular components, because now I can build a logic component and it's decoupled from security. So in literature, funcrests are known as capabilities. It's a capability to send a message. And it's opaque, it's unforgeable. That means the program can't see it. And it's transferable. Yep, so that's it. All right.
Awesome. Thank you, Martin. Okay, now working on a 30-hour time delay all the way from Bangkok. If we can please welcome Jun Hasegawa, the founder of Omise, and he's here to talk about a very cool project called OMG World Exchange. Jun.
Hello. Hey. As I'm still super jet lagged and I'm really sleepy, but I think you guys all are sleepy and also tired. It's but 3 programs more to go, and then today is finished. So I'm talking about tokenizations, and then I have, just in case, I have a note here, so don't worry, I will talk about this appropriately. Thanks for great illustrations for Horde team. Looks very young. Right. So let's start talk about the tokenizations economy, and then OMG World Exchange. So in a very short time that we have managed the tokenized significant value, hitting over 800 billion market cap. Now, a little bit, it's around half, unfortunately. It's okay. But is it big enough? So let's see this graph. At this time, crypto market has such a small portion of the total asset value relative to the fiat currency and then stocks. So as you can see, crypto is, even compared to the fiat, it's 400 billion. It sounds huge, but it's actually not really huge. So more obvious way is next. So, and an even smaller portion relative to the total asset value, including the real estate, gold and silver, stocks. We cannot see. Actually, it's less than 0.1%, so we cannot really see anything here. So, we still have a long way to go. So we still care about the asset that preceded the forthcoming asset, right? ETH is still measured by USD or some other crypto pair. Fiat was historically backed by gold, and the tokenization of different into new asset is also significant. But in the historically, it's 1,000 years ago, we are using stone as a value. And then we tokenize into other materials. But do we really care about that custodial, the asset, which is stone, is now? We don't really care anymore because we already tokenize to different asset value. So we are never asked, where the hell is my stone anymore? So we shift what we attribute the value to into new asset. But how does tokenization of an asset happen? So value asset X is now the current mainstream, and Y equal tokenized asset. And then third is the way to tokenize, and the fourth, and then become the value asset Y is going to be the mainstream asset. So let's see our historical tokenization. So stone, it's tokenized to jewelry, and the jewelry tokenized to the gold, and the gold tokenized to gold and silver currency, and gold and the silver currency to the fiat currency, and fiat currency to digital currency, right? And such as internet banking and other the asset. And then finally, these digital currencies become a cryptocurrency. So the ideal asset comply with these conditions. So one by one. The versatility, the ability to exchange anything, reciprocity, the mass access, and security, proven authenticity and ownership, and then completeness, the finality of transaction, and the privacy, preservation of private information and data, and stability, the perceived level of the risk and asset, and then scalability, ability to serve the masses. So, so assets vary in their ability to satisfy these conditions. As you can see, it's far right. Cryptocurrencies do not currently provide all of the core capabilities, but some, yes, like Ethereum. But boom, OMG Network. So OMG Network is a tool that can enable cryptocurrency to achieve acceptance. So let's take step by step. So dApps that connect to the OMG network will enable versatility of the cryptocurrency and asset, serving various use cases. Receivability. The e-wallet SDK library, which is now on our GitHub and open source, will support the receivability of the crypto by enabling anybody to build a compatible wallet. And then already several of our partners, the real businesses, that integrated this SDK, and we will see this SDK integration in the real businesses very soon. And security, rooted to Ethereum, enables security and the proof of ownership, as well as completeness and privacy. And stability. The OMG DEX will facilitate crypto asset to become more stable. And lastly, Plasma. The Plasma chain will support massive scalability of the Ethereum network. So, OMG World Exchange is coming. And basically, it's a very short word. What we are doing is bridging the gap between Bitaric's mind and your grandma. Thank you.
That's a big gap. Very big. Okay, now we have Jay Kwan of Cosmos, founder of Cosmos and Tendermint, to talk about one of the best interoperability projects going on right now, Cosmos. And there was a rumor you might do a rap like Ethan Buckman. Is there any truth to that? Oh, okay. No, sorry. Okay. We'll just talk about interoperability. Please welcome Jay.
Thank you. I think I should stand here so I can see the slides. All right. Yeah, Cosmos. So we had a fundraiser, last year, and last EDCON we also talked about it a little bit, but I want to give a little recap of what it's about, and then talk a bit about current thinking and the progress as well. So do I just do this? Next slide. All right, sweet, thank you. So, you might have seen this before. Please raise your hand if you have seen it before, this slide. Okay, thank you. Oh, nice, this is great. So, when Bitcoin came about, in 2008, it solved a really big problem, which is how to have a public ledger without any centralized control and yet have it be secure to function as a ledger for payments. But in reality, in fact, there's been research into similar algorithms since the 70s, funded by various organizations. And most of it was kind of like forgotten. So you might, so what we hear is that the BFT research landscape was kind of boring for a while until like after Bitcoin, and when people realized, wait, we can use this stuff for distributed ledgers and blockchains. That's amazing. Before, these algorithms were actually Byzantine fault-tolerant algorithms were developed for things like fault-tolerant control systems for like airplanes and missiles and so on. So it was actually funded by government agencies like DARPA. And what we're doing is bringing that back to the software world and actually implementing a BFT middleware so that it can be used for blockchains, for public blockchains and private blockchains and so on. So if you want to read a technical white paper that kind of catalyzed this project, Tendermint and Cosmos, I would read this one, the 1988 paper. It's a pretty deep read, but it's got all the components that enabled me to understand how to solve proof of stake in a different way. Yeah. So Tendermint is an open source consensus engine. It's on GitHub. The best property is that it's really fast and it's very secure. So, with proof of work, the security is only proportional to the amount of energy you expend, and because of that, you have to wait a long time for a transaction to finalize. But when you have a consensus algorithm based on public key cryptography and voting, essentially a two-phase commit algorithm, then you can have every block be final, and so you can get instant, relatively instant transaction finality. So the Cosmos Hub is built on Tendermint, and it's going to have 100 validators. Of course, you can have as many as you want. You can have 4. 4 is the minimum number of nodes. 4 validators of equal weight is the minimum number you need to be Byzantine fault tolerant, because if you only have 3 and 1 goes down, then the whole blockchain halts. And that 1/3 Byzantine fault tolerance is kind of like a natural limitation of trying to be safe in the presence of a network partition. So you might have heard the discussion about like, liveness versus safety, or availability versus consistency. I think I got those flipped. What Tendermint does, it's very opinionated, and it says that when there is a network partition, so like imagine the left half of the room and the right half of the room can't talk to each other, then the blockchain knows that, and the validators are not able to produce any more blocks. And this makes it safer for financial transactions, because otherwise, like, imagine what would happen with proof of work if there's a huge network partition. One country is going to be using the blockchain and thinking that they're on the right chain. Both countries will, or both continents will, and when the network heals, you're essentially going to have a hard fork because no one's going to be happy. So we choose safety over availability, because if it's not safe, what exactly is being available? So anyways, that's that. Oh, and we also made Tendermint to be agnostic and general purpose. So there's a network socket protocol called ABCI, which means that we separate out the logic of the state machine. So all the smart contract, EVM, virtual machine, or even if your blockchain doesn't have a virtual machine, but it's rather implemented in a native language that's compiled, that and the persistence is separated from the consensus algorithm, as well as the peer-to-peer networking, mempool broadcasting, and so on. So that separation is really nice, because what it means is, even if you don't like Tendermint and you feel like another consensus algorithm is better, you can swap it out. Right? So that's the idea. Okay, so what we're doing with Tendermint is we're creating we're launching very soon the first, one of the first proof of stake blockchains that's secured by classical Byzantine fault tolerance. Not only that, so the Cosmos Hub is a blockchain, all right, powered by Tendermint. And its job is to communicate with all the other blockchains in a secure way. So what I mean is, today, blockchains are not aware of each other because, in order to do so, you would need to get the light client proof, SPV proof, embedded, as a transaction on the other chain. But generally, this isn't done because proof of work makes it difficult, especially with having to roll back transactions. I remember back in 2013 when I was working on a crypto exchange, trying to implement an exchange in the face of blocks that might be reverted. It's really difficult. So if we have an abstraction that says there are no block reverts, there might be reorganizations or hard forks, but you don't have to worry about blocks being reverted all the time, then it makes things a lot more simple. Anyways, so what Cosmos does is it communicates with all the other blockchains using IBC. It's kind of like IPC, but it's inter-blockchain communication. Let's see if we have some slides to show. Okay, so on that side over there is TCP/IP, right? And IBC is pretty similar, except it doesn't have, it's got different headers and so on. The mechanism, let's see if I have the slide here. Nope. The mechanism is pretty simple. So the idea is first you prove, let me first describe the light client SPV on Tendermint. To prove that the last block hash on Tendermint was some hash, all you need is that hash along with 2/3 or more of signatures from the validator set. And in general, you want all the validators to sign, but you don't need all the signatures because it's Byzantine fault tolerant. You only need 67% of the voting power. And that proof, which is the signatures and the hash, proves to the other blockchain that something really happened on that other blockchain. And from that proof, that hash, you can later asynchronously provide a Merkle proof down to anything in the persistence layer of the blockchain. So conceptually, it's as if I can send you a packet, me being a blockchain and you being a blockchain, and you would know that the packet was really from this blockchain, from me, because you can tell that I signed it off on it because there's a whole Merkle proof and signatures from the validators that say so. So using this abstraction of blockchain to blockchain communication, we can create interoperable and scalable blockchains. And what we're trying to do, our mission, is to make good protocols that can be the foundation of our future financial system. So the IBC protocol that we're developing is also designed to be general purpose. You can use it for anything that you want. So, just as an example off the top of my head, you can use it to communicate like anything. So like one blockchain might say, hey, here's a resource over there. I want you to lock it because I might need it for like an hour later or something. So you can just send a message, not send any token, but send a message to the blockchain saying, this is an asset controlled by this blockchain, so please lock it up for me like as collateral. So you can do all kinds of things. Of course, you can also send smart contract calls, right? So what Martin was talking about with asynchronous packets between processes, sending that packet can be done over IBC. All right, so that's one way to scale the ecosystem. It's by having many blockchains that's coordinated by a hub so that you can move tokens from one chain to the other. Now, I want to describe here how we're going to connect to the Ethereum mainnet, right? So the Cosmos Hub is a Tendermint powered blockchain. It's running proof of stake. And in it will be a module where we record signatures from witnesses that testify to the latest state of the blockchain on Ethereum. So these witnesses are running the full node client of the blockchain, and they're signing off on it, saying, I really saw this block here. And you can imagine how we can come to consensus about, on the Cosmos Hub, that was the last block on Ethereum. And likewise, the witnesses would also sign off on what happened on the Cosmos Hub. Actually, there are two ways to do it, of course. I mean, the Cosmos Hub validators themselves are a witness, but it could even be separated into different layers. So the witnesses don't have to be the full validator set. So this is how we connect to the main Ethereum chain. We also showed a slide before, I think maybe last year, where we had an adapter blockchain in the middle. So the adapter blockchain in that slide from last year was about, it's really about making proof of work and proof of stake, BFT proof of stake compatible. So here's what I mean. If Ethereum were not proof of work, but rather it were another tenement chain, then we can actually have direct, IBC communication, and we wouldn't even need this PEG module, just for clarification. So the reason why we need the PEG module is because Ethereum is proof of work. So this way, you can have your, ERC20 token or Ether. You can send it over to a smart contract that where your tokens get locked up, and that smart contract and the tokens would be controlled by the witnesses. And so when you lock tokens into that smart contract on Ethereum, they would appear to be issued on the Cosmos Hub. And you can move them around, move it to another zone, even use it in a Zcash blockchain, say, or any other blockchain with any logic. And then you can withdraw by sending it backwards. You always have to go backwards in the same path. It's important to note that, our philosophy is not to try to create some kind of to combine many bridges and pegs together to create a liquidity pool that represents ETH. That's all stuff that can be built on top. The protocols we're designing it for a multi-hub world, because the Cosmos Hub is a hub, but so is Ethereum. And Ethereum will be connected to other hubs, and the Cosmos Hub connected to other hubs, right? So we have to think about, what does it mean to have all these pegs and bridges? How do you make it all secure? The answer is you think about the path of pegging and make sure that you always have to go backwards the same way. Here's a second thing, another way for us Ethereum holders to participate. So besides bridging to the main Ethereum net, we will also propose a hard spoon event. So copying the Ethereum blockchain and all the contracts and state that's in Ethereum with a snapshot. It's basically a hard fork, except we're not trying to compete and say this is Ethereum. We're just trying to create a new token and a new, the main difference between this, the benefit of this over bridging to mainnet Ethereum is that the peg, the earlier slide I talked about, this guy, this depends on the security of the peg. And it's entirely possible that, say, for example, if the Cosmos Hub were to get, it is possible for it to even hard fork or fail, right? Because it's only Byzantine fault tolerant, not perfect. So if the bridge were to break, then who knows what's going to happen to the tokens that are stuck in that smart contract, right? Ideally, what happens is in the future we have better governance on these blockchains to manage various issues that can arise. So, for example, even if the Cosmos Hub were to go under double spend attack and get forked, it would be nice if the Ethereum blockchain also had some mechanism to ensure that the correct, according to some metric, chain were to retain the contracts. Now, there are other ways to deal with this. One way is to have an exponential, a time-based solution where you just say, no matter what happened to this chain, usually you need 2/3 of the voting power of the Cosmos Hub or the witnesses in order to withdraw the funds, because that's just our BFT tolerance. But you don't necessarily need 2/3 all the time. For example, I have 1 minute left. I'm going to skip over that. But talk to me about alternatives to dealing with fork failure. So the other thing we're going to do is we're going to copy the Ethereum distribution and provide tokens. We're calling them photons now. We're not sure what they're really going to be called in the future. The benefit is that it doesn't depend on the security of a peg, because the intent with this this token is that it's completely managed and controlled by the Cosmos Hub governance system. So you can think of the photon as being something that the hub decides through governance. There's like a proposal process with votes and vetoing. You can go to cosmos.network to learn more about it. And I also just want to, here's the status update. I've got 1 minute left. Check out the Cosmos SDK. It's like a fourth iteration of what we want it to be a really good blockchain framework. And we've arrived at a model that I think is really good and is probably going to be the final, it's our final version. And we'll be launching with it, and the Cosmos Hub is built on it. Object capabilities. So that means, for example, least authority. Only passing in things to handlers and methods that it needs to know, so that even if you were to try to import, like a third-party plugin that was buggy or malicious, it only has a limited amount of damage that it can do. All right. And also, it's very modular. It's got all the components, like the persistence layer and all that are very well separated to enable fast innovation. So the Ethermint the next iteration of Ethermint is being built on top of the Cosmos SDK. So I think you might have heard a talk from Alexei recently about the work he's doing on the KV store, which will all be reflected eventually in the Cosmos SDK as well. Go to the Riot channel, because we're just starting this new refactor up, and if you're interested in getting your smart contracts running on the Cosmos SDK and connected to the Cosmos ecosystem, this is where you want to track the progress of it. And here are some more links, so you can read more about Cosmos and Tendermint and what we're up to. Thank you very much.
Awesome. Thanks, Jay. Okay. Thank you. You need this? Now the grand finale, I guess. If we're going to put together, all this talk about scalability issues, let's put together a dream team of scalability people on stage together and to jam it out. So does everyone know who's coming? Vitalik's coming up. Who else is coming up? Carl's coming up. John, I know you're going to MC it. Phil is coming up. Justin Drake is coming up. Oh yeah. Shay Wei is coming up. And of course, Vlad, get in there. And Joseph. Are we going to bring some chairs? John, this is for you, my friend.
Appreciate it, thank you. Let's just wait for a minute while we get the chairs. Thank you.
Classic. Oh no. Shardirium? Our group over here. Yeah, Shardium. It's a fun group.
All right, should we get started? So thanks for coming to this panel. Today we're going to talk about scalability, the hot topic. So before we get started, why don't we just do a little quick intro and maybe share one scalability research problem that's been keeping you up at night.
Does the mics work? No.
Okay, I'm Justin. I work on sharding. It is on sharding research. The main problem that keeps me up at night is data availability. How do we solve it kind of conclusively? Still thinking about that one.
Hi, I'm Vlad. The main thing that keeps me up at night is just I still don't know how scalable it can get. I don't know I can't even quantify the possible scalability of the blockchain really.
What keeps me up at night? I'm Phil. I'm a second-year PhD student at Cornell, and I would say right now it's resource pricing and how to build sustainable pricing models for example, computation on the EVM in the long term.
Hi, I'm Carl. The scalability problem that keeps me up at night is not that many people know how to solve it, but it's not that hard. No, it's hard, but we can do it. Vlad.
Committee selection, shard crosslinks, random beacons, hash onions, full proof of stake, notarization, that's data availability proofs, that sort of stuff.
Do you sleep?
Sorry, Philippe, what's this word that you talk about?
Okay, so my problem is more about implementation because when these people are thinking about all the research question, we are the one who will do it. So that's my problem.
Oh, we have more for you. Hi, I'm Joseph Poon. What keeps me up is oftentimes a lot of people make claims about scalability and they're not really saying what the trade-offs are. And oftentimes the trade-offs are a certain kind of centralization, which is inherent trust in certain systems. And oftentimes you see things with designs such as, oh, it'll run really fast with this assumption. And oftentimes they bury this assumption and they really put in the header a lot of the marketing speak and they bury a lot of those. And oftentimes a lot of community confusion can result. And I think a lot of the projects out there do this, and that's become a really, really big problem because it's becoming this issue around very significant claims, resulting in very, very significant degrees of centralization and worse trust.
So can I start this panel off on an adversarial foot and say, are you talking about Lightning Network?
No, I'm not. I think, so when you're dealing with a certain measure of trust, it's not, Lightning doesn't have that constraint. When you're talking about dependence upon certain things like a scale-free network, when it comes to having larger nodes, I'm not talking about that specific aspect. I'm talking about issues where it's just this thing runs great on 10 validator nodes. We can have a trillion transactions per second. LOL, it's going to be great. And then everyone talks about it on Twitter and how great it is.
Okay, so even simpler, yes.
Yeah. Okay, so I think that's actually a great segue into something we can talk about next, which is trade-offs. So maybe we should think a little bit about what are the various approaches out there that try to solve scalability. Take the examples, maybe explain what kind of trade-offs they're making in terms of decentralization or what have you. Anybody can take this question.
I just want to say that this is kind of what I was saying earlier. I don't even know the trade-offs. I don't know the best trade-offs that exist. I still don't think we've gotten there to this trade-off surface that is at the ideal trade-off surface.
Maybe we can identify a couple of the obvious dimensions first.
Well, there's the ones that exist for consensus protocols.
Sure.
So there's that, which basically says at very least there's a trade-off between the number of nodes, the latency to finality, and the overhead of the protocol.
So I guess an example, the Lightning Network has trade-offs in that For example, you need a secure routing algorithm to find routes in your payments, which could be a privacy compromise vector, as well as a funds loss vector potentially, like an availability failure vector. And also it requires users to stay online or to delegate that trust to somebody else on the network, which is in and of itself a centralizing trust vector. But it does achieve, for that trade-off, instant finality, at least assuming those assumptions hold, which is quite a valuable property.
State channels versus plasmas, I find a very interesting comparison because, like, in some ways they are both similar kinds of technologies because they have like basically on-chain games where each user's expected outcome from the game can be affected either mostly or entirely by off-chain messages, which is a really cool scalability strategy. But the way that they implement it and which tools they can use and not use lead to some fairly different outcomes, right? So, like, for example, one of the really nice things about a state channel system is that it's not just a scalability solution, it's also a latency solution. And inside of a state channel, because you can change the expected outcome of the game with just off-chain messages, you have instant finality. But one of the trade-offs that you have to deal with is that in order to add people to a state channel, you have to have on-chain messages. With a plasma system, on the other hand, like, you can just add people, remove people, and like whenever you want. But in order to get any kind of finality, you have to actually wait for the plasma Merkle root to get into the main chain and for that block in the main chain to be finalized. So I think like the differences between what use cases make sense for different kinds of state channel networks, what use cases make sense for like different kinds of plasma chains is one of those things that could be analyzed some more.
One interesting trade-off is regarding the use of non-quantum secure crypto. So, for example, snarks can be really helpful for scaling, but then do we want to incorporate them at the protocol layer given that they're not quantum secure? Another interesting one is BLS signatures, kind of similar dilemma.
And just to add on to that, like replacing some of those complicated cryptography mechanisms with crypto economics and like with kind of like incentive-based games, that is definitely a trade-off, just like building on.
Yeah, I think definitely want to echo that one. I think there's a attraction to using fancy crypto, and I think it's perhaps better to do something like defense in depth, where you have perhaps fancy crypto to help you, but as a backstop you have iterative or some type of interactive game that's really backstopping everything, and at the top you can maybe have like secure elements or something like that if you want that. The other trade-off, I think, to get to the topic, I think making trade-offs around presumptions of speed and latency, I think should be one that one is willing to make under certain circumstances. I mean, this is a matter of personal opinion. But yeah, I think it's always a discussion on like perhaps you can have maybe the base layer be fast and that resolves problems across above the stack, or you can make it different types of constructions and different complementary constructions across layers with trade-offs.
Cool. So I'm sure different people got different things from that, but I think one thing that's clear for everybody is that the design space is vast. So I think one thing that might be helpful is we can take a step back, and can we kind of each take turns, maybe somebody choose channels, somebody choose plasma, somebody choose sharding, and describe it in like 30 seconds and a minute on what the goals are, what the key insight is around that approach, just as a background.
I guess the key insight for me for sharding is to try and amplify the security of the main chain to the shards. And one of the key things that we're doing there is fast shuffling of the validators. And one way that we achieve this fast shuffling is really by decoupling the state layer and the data layer. The state layer is what bogs us down and prevents fast shuffling. The data layer is totally free to shuffle at will.
So just to attempt to describe plasma, a distinguishing feature between kind of plasma or general state channels is that plasma you have this kind of like exit mechanism, and this is also different from sharding, and so you have, it's not an n of n multisig, it is open participation. You can learn things about the chain, it's off-chain. We need to, having the kind of, understanding how to explain these things and differentiate them in simple terms is very difficult. But we need to do it, so please, Vitalik, actually, please, go, take it over because I'm not doing the best job.
What am I explaining?
Difference between plasma and, yeah, just describe plasma.
Okay, so I think as I kind of briefly alluded to before, right, there's this fairly large class of layer 2 scalability solutions, and the common philosophy behind this entire class is that you have a game, and a game in the game theory sense, not in the Pokemon Go sense, right, where the payoffs of that game are processed by an on-chain smart contract. But the payoffs of the game can depend on messages that have been signed off-chain by different users. And the interesting property that these games have is that you can make very large and complex changes to the expected outcome of the game. So this could be either the Nash equilibrium of the game or the expected outcome of the sense of what is the minimum that you're guaranteed to get if you personally act in your own interest regardless of what everyone else does. But regardless of your model, the expected outcome of the game can change based on either just entirely a series of off-chain messages or a series of off-chain messages plus a very, very small amount of data like an on-chain Merkle root. And what this lets you do is, well, basically, if you have a large number of users that are all part of this system and that have and that expects to get some kind of payoff from this game, then if they can use off-chain messages to basically transfer their rights to payoffs inside of this game, then doing that transfer of rights off-chain is equivalent to a payment and is within the context of some model, equivalent to doing an on-chain payment, but without actually having to do a direct on-chain transaction for every single transfer you want to make. And so, state channels is definitely the earlier version of a technology that tries to do this. And the way that it does this is you basically have these channels between pairs of people, and the game basically says whoever can come up with a ticket that was signed by both parties with the highest sequence number wins. And based on that fairly simple ingredient and based on networks of channels, you can create these fairly complex structures. We can have entirely off-chain payments that kind of finalize instantly. And then Plasma is this technology that allows this additional secret ingredient, which is basically you can take a huge pile of data, hash it, and then publish the root of the Merkle root of that data on chain. And if you can use that secret extra ingredient as a construction in clever ways in order to get much better capital efficiency and much better user inclusion and substitution properties, but at the cost of other things. And so the study of all of these kind of off-chain games basically has to do with how do we take these different kinds of off-chain ingredients, how do we structure these games so that the kinds of state changes that we want to make can happen as efficiently and as securely as possible.
Can I dumb that down 10 levels? Which is that you have the main chain and a plasma chain. The plasma chain puts Merkle roots on the main chain, and the users have the guarantee that as long as they're online and watching the plasma chain, as soon as something goes wrong on the plasma chain, they can go back to the main chain and are guaranteed to be able to withdraw their coins using Merkle proofs of what has previously been posted.
And something that's interesting is that this is actually resembles sharding in some ways where you have some kind of deposit, some kind of crypto economic mechanism where you're securing a off-chain chain with a some kind of root chain-ish, but at the same time, I think the kind of key difference is that for the source of truth for Plasma, the source of truth is really the Ethereum chain, and the state is really held in the Ethereum chain, and you can always exit onto the main Ethereum chain. Whereas in sharding, the kind of security is just the all-encompassing, right? It is tightly coupled to the security of the root chain, so it all fits in one.
And one thing on an abstract level that's fairly interesting with a lot of this movement in terms of what we're talking about in relation to sharding and plasma in particular is that we're talking about, and you know, the work with Jay Kwan with Cosmos as well, is there's a lot of current work in relating the relationship between sets of data which is not completely validated by all parties, right? Because if you look at the way the blockchain works today and how we understand it, is that everybody in the room computes everything together. You know, everybody in the world, rather, computes everything together, and there's a certain level of assurance, in particular in relation to data availability. So, you know, when Vitalik has been talking about data availability for the past, you know, year or two, this is the fundamental problem that we're basically facing today. And that's why, you know, there's a lot of shift in the narrative within the Plasma space between, you know, Plasma Draft, Plasma MVP, and Plasma Cache. And it seems like, you know, a lot of the design constructions in Plasma Cache seem more robust than there's certain types of adversarial constructions with certain types of trade-offs in terms of, you know, ease of understanding and things like that. That may seem to be coming to the fore.
Cool, thank you guys. So as you can see, like different approaches have different complexities, and I think as we talk to each other, certain things clarify, right? I think in the beginning it was started very technical, and then certain things bubbled up, like the ability to exit from like Plasma chain to the main chain is something that gives you the scalability. That's kind of the key insight. So we need to continue to do this for all these technologies, but maybe what we can talk about next is we have a lot of different scalability solutions, like base layer sharding, we have Plasma, channels. How do they all interplay? Like what's going to come first? Do any of them kind of have benefits from both being online? How should we think about this?
I think the general rule of thumb is that everything composes, and the design space just keeps on expanding. So you can do kind of payment channels on top of Plasma, on top of sharding, do everything together.
You know, while I kind of agree with that from the point of view of like experimentation and distributed systems, I also think like economically the story isn't so simple, because the layer 2 solutions create failures that are more profitable in layer 1 solutions that they rely on. So if you are able to censor layer 1, then you can steal from payment channels. If you're able to censor layer 1, you can game Plasma, and that increases the profitability of attacking layer 1 with censorship. And so I don't think that the security of these things are independent. In fact, I worry that layer 1 solutions will be compromised by layer 2 solutions. And you know, I don't think it's that simple. But I do you know think that like we should experiment with things on layer 2 just in case layer 1 governance breaks down and we can't do anything to layer 1.
So just to kind of touch on how they all kind of compose, one thing that you can do is you can like take a like Plasma cache chain, for instance, and you can shard the Merkle tree, and then you know have validators that are able to they validate just subsections of the kind of like overarching Merkle tree, and so you can get like really high throughput and keep it kind of proof of stake. But at the same time, it is true like that proof of stake value may compromise the root chain, and you are relying on the root chain, so it does get tricky. But like all of these designs definitely do mesh really well, and a vision of a sharded Ethereum supporting sharded Plasma cache chains that are running state channels is like kind of cool, I think.
Yeah. Agree.
So I think there's the same thing is that the Plasma chain and the shard chain, they are both the like kind of their parent chain. So aspect of the implementation part, that maybe the importance of like kind will be more important than ever before.
And I'd also like to add that a lot of the constructions that we look at across these solutions do have similarities in the tools being used, because oftentimes you're facing similar problem sets. So it's less look about these as individual products. I think that may be the wrong approach. It's better to look at these about the individual approaches within these different designs. And that may help you reason about this a lot better, because it sort of doesn't matter what wins, so to speak, because they all do similar things and they all achieve things in somewhat similar ways. So, I would recommend, like Carl's work with, cryptoeconomics.study, where it's about like, what are these individual tools in your toolbox? Because that's the relevant aspect if you're a developer to really, really look at. It's just, okay, you face these like, liveness constraints. How do you resolve that? You face these issues around, data availability. How do you resolve that? And that's one way to really, really reason about things in this space.
I don't care what coins are in my wallet. All I want is decentralization and crypto economics.
But we do solve different problems in these different solutions. We do have problems in common, like availability and validity, but also some problems are very different in like terms of the semantics and the authentication and the security guarantees and the security models. I kind of have a hypothesis that if sharding scales enough, then we'll see state channels and plasma used only as a low latency user experience improvement, as opposed to for actually scalability.
I think I agree with Vlad on pretty much everything he's said on this issue. So these things, they do compose at least in code. Whether their security guarantees compose is a very open question. I don't think we understand any of these technologies by themselves, never mind when you're like doing plasma on a sharded blockchain or when you're sharding a plasma blockchain. So I think R&D is great, and I think they should all be explored in parallel, and that is the right way to develop technology. But in terms of would I deposit my money on an exchange that was running in a shard in like the first week it was running? Probably not.
So something that we talk about internally is why even go about this layered approach where you have base layer sharding and you have plasma and channels on top. And could you talk a little bit about the trade-offs between having a fairly complex and layered approach to scalability versus something around just block sizes or lightning networks? Why go through the complexity for this? Like, why are we doing this?
I think, first of all, one important point to make is that, like, with all these different scaling solutions, right, the point is that we're trying all of them at the same time. And so if for some reason, like the trolls are right and sharding gets delayed by 5 years, well, guess what? Next year we still have, like awesome state channel networks. Like we still have Ryerson, we still have liquidity, and like all of the, and like Keller and whatever else is being built. There's we're still going to have plasma chains. We're still going to have things like Loom. We'll still have OMG. We'll still have people building, like systems that have that benefit from the scalability advantages of more centralized consensus algorithms like a consortium chain or DPoS, but at the same time still benefit from being rooted in a properly decentralized base layer. And like even if like state channels or plasma get nowhere, and like there's still the work on sharding, right? And if the trade-offs of plasma and state channels are not satisfying for your particular application, and you do want something that still feels like just a blockchain you can dump stuff on without really thinking about it, well, that's what sharding also gives you. So it's part of the kind of seeming complexity comes from the fact that we are trying to take this kind of broad and horizontal approach where, like, ultimately, if even one of the approaches works, then great. But if all of them work, then they end up stacking on top of each other and create something that's like really scalable and high performant. Another thing to keep in mind is that like the more complex approaches are important because like we are actually trying to create something that scales while preserving the same properties that we value in blockchains that exist today. Like, like client-side validation, the ability to verify that for yourself that any particular transaction was executed correctly. Like if you have one of these fancy blockchains that can do 100,000 transactions a second, and they can do that because they don't even bother to have a Merkleized state tree, well, guess what? You can't verify the whole thing without verifying the entire blockchain from history, which basically means that it can only be verified by like 5 guys in the entire world. So if you actually want to break through the scalability triangle and you want to have a system that is as client-side verifiable as possible, as decentralized as possible, and as difficult to attack by like small actors, like 1% attackers and so forth as possible, then yes, you actually do have to think, but like after the research that we've made over the last few years, like I'm actually at this point really convinced that, I mean, first of all, the ideas exist, and second, for every single problem, multiple solutions of different kinds exist, and now it's just a matter of figuring out the optimal trade-offs and like building out the peer-to-peer networks and implementing them.
I think one of the reasons that we've seen so much emphasis on the layered approach is this concept of permissionless innovation that's really popular in blockchains. So you do need permission to change the consensus algorithm in these systems, but you don't need permission to try to scale out another layer or try to prove the concept of your technology. I think kind of speaking to Vitalik's point, there is very much an open question right now of whether there is a one-size-fits-all scalability solution that you can just bring into layer one and everyone is happy. I think, for example, that's what Vlad is trying to find with his work.
We can't prove we can't do it.
Okay. But until then, these solutions do have trade-offs, and like doing them at another layer allows you to explore those trade-offs without locking yourself in. So.
Yeah, so quick question, just to kind of dig a little bit deeper. So what you mentioned about the original intent of a blockchain technology, right? Thinking about client-side validation, how do we know, that's really a constraint on the scalability that we have today. The more decentralization we want in the system, the harder it is to scale. So how do we know, how have we verified that people want this feature of infrastructure?
I really don't like that argument of the more decentralization we want, the harder it is to scale. I think scalable systems have more stakeholders by their very nature and therefore are more decentralized. And so like I strongly reject the narrative that has come out of the Bitcoin camp that sort of increasing resource requirements inherently leads to less decentralization. I think that's like a bunk argument and we should not spend any of our time on it as a community.
I mean, regardless of that, that opinion, right? Even internally, we have like the scalability trilemma where we literally have scalability and decentralization on one rung. So I don't think that's necessarily a fact. I think it's worth talking about, exactly. Like I think this is the type of discussion we need to have.
But I think there's also different ways to mitigate that, right? Like I think the work that, you know, Dad Robinson and Vitalik worked on with Plasma Cash, and Carl and various people online, is that like essentially you could say, yes, you can have client-side validation, but you selectively have client-side validation within a certain subgroup. And that allows for incredible scalability when it comes to that particular aspect, with the benefit of full validation and ensuring that you are responsible for your own data kind of thing, which is what we have right now.
But definitely, like you asked kind of like a deep governance question of like, how do we know what we want out of our protocols, especially the layer one ones that we all have to agree on. And normally like the philosophy in Ethereum is general purposeness and abstraction so that we can serve everyone's needs with a protocol that is flexible enough. And you know, the extent of the general purposeness of Ethereum, you know, has yet to be seen. And I mean, hopefully that can avoid a lot of these political questions or like these governance questions about like, oh, do we care more about like performance or decentralization, assuming that is a trade-off.
It's not purely a governance question though, right? Because imagining a validator as a server versus like your laptop is the technical question and a product question too. Maybe we should just broaden this question and kind of like think about, you know, what are our thoughts on this issue?
I think there are a number of deep questions that we're striking at here, and I think Vlad is right that in a way, like what is our product is a governance question to an extent. And it reminds me of a pretty like simple but deep question I was asked at some point by a fellow researcher, which is when you're doing this transition to proof of stake, like how much security do you actually need? Like what is the dollar value of security that you want to have? And does the person that's doing $5 transactions on Ethereum necessarily agree with like the person who's doing $100 million transactions on Ethereum about this? So I think even answering that like very simple question is a very hard governance question.
That is fair. Anybody else have thoughts on this topic? This broad topic?
We do have like these techno governance questions, right? Where they're like both technical and governance questions. Like, you know, can we be expected to have a server that's stronger than like an i7? You know, like a single i7? Like, I'm not sure. You know, if people want to sign up to a blockchain where there's a requirement. But on a layer 2 solution, you don't need to participate in this governance stuff as much. And you can just roll your own, and no one really mind. Kind of like Phil was saying with the permissionlessness.
So I heard someone say recently that decentralization gives them a warm and fuzzy feeling when they're using a decentralized blockchain. And so I feel like that's my best measure for my personal, decentralization. But at the same time, you can get fooled and get the warm and fuzzies when you're like working with Google, maybe. So I don't know, maybe this is like guessing.
Yeah, I think there's going to be a temptation in a lot of these systems to centralize for scale, and I wonder how much do people actually value decentralization?
I think they'll value it more if they understand how it works, and they understand like, okay, this is decentralized and this is what centralized means, and these are the trade-offs that I'm making. So that's why education is important.
So we're going to switch topics a little bit. We mentioned how consensus comes into play. So to the people that are kind of watching online, how does our move to proof of stake have to do with scalability? Is it a scalability problem? Is it not? Is it enabling sharding? Is it not? Like, how do we think about this?
Well, I think the main way that proof of stake helps sharding is by allowing us to sample validators to shards in order to delegate responsibilities like checking if blocks are available or valid or forming consensus perhaps. And so it's easier to sample and assign validators to do work in proof of stake. And that's like also why sharding is going to be proof of stake even if it's during a proof of work blockchain. But the transition to proof of stake, generally speaking, is not a scaling solution. It's a security and efficiency and usability solution. And then sharding is like, somehow at least abstractly independently of proof of stake. But sharding with proof of work is more difficult because at least if you allow any miners to mine on any shard.
Yeah, one of the things that proof of stake unlocks is this random beacon where you can have low variance and short periods. So that's a nice thing to have. Another thing that proof of stake gives for a sharding solution is finality, cryptoeconomic finality. So you can take checkpoints in the shards, feed them back into the main chain, this gets finalized, and the shards kind of benefit from that.
Yeah, that's great. That's an excellent point. Asynchronous finality is impossible with proof of work.
So another question, we talked about how this parallel approach of trying a lot of things at different parts of the layers is de-risking the overall scalability efforts, right? So if you're imagining 12 months in the future, there's more scalability and there are more dApps or any kind of applications built on top. First, what do you imagine those might be, kind of like the low-hanging fruit? And two, which scalability solution do you think would be effective by then or useful? If you had to guess.
Yeah. So like what I would probably want to see in a year is like, number one, a lot of like, at the very least, like exchanges, like companies, other institutional actors, maybe eventually a central bank or whatever, building a plasma chain. Because I actually feel that plasma chains might actually be the right compromise between like decentralization and efficiency that those kind of actors need. So rather than a consortium chain, and a consortium chain could also be a plasma chain, right? But like a centralized server that's a plasma chain is also by itself something really meaningful and actually quite easy to deploy. I'm hoping to see there be a lot of applications that are based on state channels. Like I know Funfair has launched already. I mean, I know SpankChain has already done a lot of stuff, and hopefully one of these general state channel software packages, would be available and people would be building on it. Hopefully the sharding network will be actually online and you'll in some early stage and you'll be able to even stake ETH on the main chain, and even if it's just a chain where you can just shove a whole bunch of data on it, people will be using it for decentralized Twitter. And we'll actually be able to see all three of these things in action. And at the same time, we'll be able to see a lot more stuff based on ZK Starks in action, and we'll keep going from there.
Cool. Any other guesses?
I really think that there are a lot of possibilities for building decentralized applications that are also user-friendly and just like using different tools like in a smart way. And so like in the next year, it would be really nice, like while the decentralization space has a lot of hype, has a lot of money, like that we actually like produce something and get something out for people to use. And so it would be awesome to see like user-friendly apps that don't actually take a long time for transactions to go through. I don't want to use Etherscan to look at my like transaction status. Like I want to see like ding, it's done. And like, okay, once again, it's like, is it centralized? Is it decentralized? But we can make it decentralized and we can make it like user-friendly. Those are not, you know, diametrically opposed.
Just because you can make it decentralized doesn't mean it's the model that's going to win in economic competition, though, right? So in my opinion, in a year, nothing substantial will have changed with regards to fundamental blockchain scalability. You'll probably have a few exchanges and things like this, piloting Plasma-like deployments. But hopefully in 5 years, we'll see fundamentally new architectures that are really delivering huge throughputs. My intuition is that we'll see this on one of ETH's probably smaller competitors first, just because they don't have to deal with backwards compatibility or the struggle of sort of patching a billions of dollar network in production, and they can just sort of start from scratch and say, like, here's our throughput test, it's high. So I expect to see a lot more solutions, and hopefully within like 3 to 5 years, these solutions will have a huge impact on like the large blockchains that are already operating.
Yeah, that's my worry as well. I think the pessimistic scenario where neither Plasma nor sharding is really ready to use in 12 months is maybe like 25% chance. And for all of these like tens of thousands of developers building dApps on top of Ethereum, I feel you. And I guess one way to contribute is just to, you know, learn more about the stuff and suggest new ideas. And we have this research forum, ETH Research, which I invite you to join.
Also side chains. We'll do, you know, dApp chains?
Dap chains.
Okay, well, non-dApp specific side chains, in my opinion. Sharded ones.
Okay, so one of the last questions from me. So Vitalik, you recently tweeted sharding is coming. So what does that mean? And also broadly, there's a sharding team here. What is the state of sharding today? What are the different phases? What should kind of the community expect?
So sharding is an Ethereum scalability solution. Coming is the present participle of the verb to come. And the word is just means like something is something. No, like basically I think like we're at the point where I think as I said earlier, like I don't actually see any fundamental roadblocks that say, you know, like, oh my God, sharding is going to be impossible because of this, right? Like I feel like the core problems are solved, and on the research side, what we're trying to do is basically figuring out how to optimize it and figuring out how to make it more efficient, because, you know, we don't just want a scalable blockchain. We also want a scalable blockchain with fast confirmation times, a scalable blockchain with fast finality, a scalable blockchain with good light client properties, with good user experience properties, and one that has properties that we know that, you know, like we're not going to want to just go back on and change all over again in 3 years' time. And so, like, a lot of the stuff that we're working on right now is really much more on that kind of incremental side. And and also, like, a lot of the work that remains is also on the development side, right? So on the development side, like, basically, I mean, if you saw the Python proof of concept I tweeted out, right? Like, that's basically like 350 lines of Python that implements like a very large portion of the logic of a node that would hook onto a sharding network. What does it not have? It does not have a real peer-to-peer network. It does not have a a fully implemented proof-of-stake beacon. I mean, especially it doesn't have a really implemented peer-to-peer network, and like that's one of the things that does not really have fundamental obstacles, but I do expect is going to be a long and hard development slog to like actually finish to perfection. So I think, you know, like we really are at, you know, continuing to move through this kind of critical juncture where the remaining challenges are much more and more toward like the finer details.
Yeah, I mean, in terms of specifications for sharding and things that developers can use to actually build the stuff, we had a design like a month ago, which we've now scrapped because we had all sorts of new good ideas. And I think there will probably be a new spec, like semi-formal spec coming out in 1 to 2 months. And I think that's a good opportunity for anyone who wants to contribute to sharding to read the spec and maybe find a team, because there's a bunch of teams that are starting to form to actually build out sharding.
Okay, the last thing I'll do is something we tried at another conference, which is to switch to moderator. So Joseph or Carl, do you have questions for the rest of the team?
Oh man. Wow, that was I had no preparation for that one. I think one of those questions is, I think we talk about, you know, the value of decentralization, and you know, I guess one of the, I have another question later too, if you have another one, but I guess this is one I care about right now since it's relevant to the topic that we've been discussing. Is, you know, people are going to be pushing for, you know, things that look decentralized but may not be decentralized, perhaps in the coming year. How can we as a community interact with that? How can we reason about that, that sort of process, presuming something should be decentralized?
I mean, one part of the solution, I think, is we have technologies like Plasma, which make it easier to build things that are semi-decentralized, right? And so, like, for any kind of like crappy semi-centralized, super scalable server thing that someone comes up with, you can generally come up with a version that is that, but it happens to have more actual security because it's a Plasma chain rooted into Ethereum. So, like, I actually do see that as being a fairly important short-term thing. You know, as I mentioned, you know, we already see things like Loom that are trying to move into that direction, and I think, like, especially in the short term, it is a really promising one. I mean, another thing is that I think, like, in the longer term, right? I do think that the weaknesses of centralization are going to show themselves, and I think that, you know, like, as something like, you know, like all of these new kind of more political consensus algorithms that involve, you know, like people making big campaigns and voting for delegates and so forth, like, we've already been starting to see the failure modes of some of them, where you have people, you know, like trying to buy votes, trying to do things like, you know, like set up big campaigns and try to get everyone to vote for them, like trying to get the exchanges that hold other people's money to participate in coin votes for them and so forth. And like those disadvantages are real, and I do think that in the long term those disadvantages are going to show themselves. Now, are those disadvantages going to show themselves in time? Like, before those disadvantages show themselves, could there potentially be a very huge price bump? Well, yes, possibly, right? Like that, like, welcome to crypto. But like, in the long term, you know, like, I do think that is going to happen, right? Like, if that doesn't happen, then, like, basically the needle is going to keep on moving towards centralization, and a lot of the things that we're going to get is just the same stuff that exists now with a little more cryptography on top. So, if that doesn't happen, then, you know, it is going to happen. And decentralization is one of those technologies where the benefits of it don't really necessarily come in the normal case. They come specifically in the kind of tail case where something unexpected happens, and the stuff that, and like a whole bunch of other things suddenly reveal themselves to be fragile, and it's like, oh wait, 5 exchanges get hacked, but one of those exchanges just happened to be a Plasma chain, and on that one exchange, people can get their money back. Oh, now I see what you meant by that decentralization thing. So, like, it could end up being a moment like that. Like, I think it could actually end up being that, you know, like, if the benefits of decentralized solutions are real, then they only will show themselves after some period of time, and that is something that we have to be prepared for. Before then, like, I do think that trying to really working hard on solving the various user experience kinks and maximizing usability is something that's important.
So Joseph, first I want to thank you for asking that question, because when John did the own moderator prompt and I hadn't heard it either, while you were sitting there thinking of things, my mind was literally screaming out, like, how do we communicate the value of decentralization? So, awesome. I think Vitalik's point is pretty great about decentralization having some inherent advantages, but I don't think we can necessarily rely on that because, like was mentioned, there's a question of will it happen in time? Will people maybe be drawn by the convenience of centralized services and maybe the economic superiority of these services in the short term? I think what we need to do as a community before we start communicating the value of decentralization to people is actually define decentralization and what it means to us, because we don't even know what decentralization is. So like pointing at other people and saying they're more centralized is kind of like a know you type of game. So I think we need better empirical metrics and to communicate the value of those metrics to those users. And I'd point to the earn.com Medium post on quantifying decentralization. So maybe Google quantifying decentralization, earn.com, as a good way to start that discussion. But it's far from a final set of metrics, and we need a lot more discussion on this.
I have another question.
Are you saying
How much time do we have?
We have all night, right?
Brace
So,
yourselves.
I was talking with John before. John reached out to me before the talk, and we were just like, "Oh, I might ask you a question." And I think he was alluding to something very specific. I don't know. Were you? I was thinking maybe we could ask the same question that we asked at Economy, and that could be a lot of fun. Right? Right? Do you want to ask it?
You can ask it.
Oh, okay. We talked about this in the economy, but because we have a couple new people here, I think it'd be fun to continue this, and maybe there's an iteration of it for each of us. As there's a lot of mechanism designers here on stage, and the interesting thing about mechanism design is each of us have our own personality and approaches to this. We agree on some things, but differ on other things. And it's interesting because if you look at, those of us that have been in the space for several years, there's a certain tendency and approach to things. And, the question is, what is in your prior life experience that really formed your approach in terms of the mechanisms that you design today?
reading the Old Testament? But,
for relevance, this is very true because Vlad likes very punishment-based constructions, group punishment-based constructions.
But recently I started believing in forgiveness also. So if your Byzantine fault wasn't the one that caused the failure, you'll be off the hook. But otherwise, I'm pretty ruthless.
An eye for an eye makes the whole world blind, but 0.8 eyes for an eye actually converges pretty quickly.
So in general, in terms of mentality, I guess I'm pretty optimistic and I care for serendipity, and I think, I just believe it's possible and I try and make it work. At least that's in the design phase. And then kind of in the specification phase, implementation phase, I take a much more pessimistic viewpoint. And going back to the previous question and Vitalik's notion of the tail end, that some of the advantages only reveal themselves in extreme situations, I guess for me the most extreme situation is like World War III. And I would like Ethereum to survive, to continue running, even in the context of World War III and like a state government putting a whole army and killing all Ethereum developers or something.
Is that a proposal or? So for me, the answer is that I grew up in New York City my whole life until I left for 5 years when I was 18. And everyone I know has pretty much always worked on Wall Street or with Wall Street in some capacity. And I grew up in sort of downtown Manhattan as an outsider in this world, watching it from the outside in, despite the fact that many of my family members work there. So for me, a very big issue, and I think a lot of the problems people have with the current system is surrounding fairness, and especially surrounding rent extraction from these systems. So I do believe in sort of the capitalist ideal of building efficient marketplaces for some problems, but I also worry a lot about where are the hidden ways that users are getting taxed and where is this profit going, and how do we make those clear to the user, and how do we make that as minimal as possible to get the user the services that they need.
I also grew up in New York City. but none of my friends were like in finance. I kind of like grew up really close to Harlem and went to kind of bad schools because I'm dyslexic. And so like all my friends, basically they seemed like the same smart people that were around here today, but they like their background, their culture is very different. And so like what motivated me was just like growing up watching the people that I'm surrounded with change and going from being like a minority to being a severe majority. And that kind of influence made me realize that there are these intangible power structures that exist, and like maybe they're caused because of some kind of like, you know, chain reaction of effects, and maybe it takes time to reverse damages done to different communities. But like I personally feel the like strong impact of, you know, abuses of power, and so my mechanisms are like, okay, we can either, you know, live horrible lives and like continue perpetuating hatred and bad things, or we can like kind of be optimistic and hope that there's a way to change, because if there isn't a way to change, then that would kind of suck. So yeah.
So for me, I moved around a lot when I was a kid. So I grew up in, I don't know, lived in 10 different cities or something like that. Grew up in LA and Korea, went to school in the East Coast. And I've just been in a lot of different rooms with different types of people. Like, this is a group of people. I was also in Silicon Valley. I was also in Wall Street. I was also studying economics. And as I see different pockets of people, what I really believe in is kind of what unites everyone in the same way. Like, how are we all the same rather than different? And what I believe in is, like, how do we create the same opportunities for everyone, no matter whether you're rich or poor or from this country or that country. And I believe in like individual sovereignty, like as in like if you really work hard, you can kind of get to the places that you want to go to. But I believe in this technology, and what affects me is I believe that the minimum amount of opportunity, infrastructure, public infrastructure needs to exist so that everyone has the power to kind of learn to go after what they're passionate about. And I think this technology really aligns well with that. And it's been an amazing experience to meet all of you and to talk about these issues across technology, economics, and philosophy, and all that. So it's been amazing. Thank you. Is that it? I think. Unless somebody else want to go, share. Xiaowei, maybe. Well, you could be the closer.
I can go in the Xiaowei. So my background is, I'm probably one of the first people that grew up with the internet, and from the start, and playing video games, a lot of trust dynamics and the belief that perhaps you can, by having less trust in systems, that allows people to have long-term greater trust. I think that's sort of the philosophy that I have.
So I come from maybe a second person that come from Asia here in this table. So I think the background of our education and what's the culture somehow influence us to make the decisions. And I feel very happy to have what we have now, this community, and what we're going to have. So let's see, the final goal is that Ethereum will achieve our goals. So that's how we make a decision. We have to consider about that, the whole picture of every design decision or the governance decisions. That's it.
I think we're out of time. But thank you so much for listening about scalability and random things. So thank you.
All right, everyone, that was a big day. Big round of applause for today, everyone's speakers, for yourselves. Rest up. We got 2 full more days. Long, fun days. Thank you.